Solubility product. So what's the big deal with this? Just how well does something dissolve in something else? That's the solubility question. And I think one of the more interesting ones is this greenhouse effect, right? Because that's a solubility problem. The ocean is sucking up 8 gigatons. Now you can read about this and to get an idea what 8 gigatons of carbon dioxide is, but the ocean is saving our behinds right now. However, if you take a look at some of the research, this came out not too long ago, and the sense is still kind of out there in the news that global warming has stopped. Woohoo! Right? I mean, look at just this flat line. Things are supposed to be warming up, right? The flat line. We're safe. Woohoo! But they don't show you the rest of the plot, right? They zoom up on what's interesting. But if you look at it as a trend of since 100 years ago, it's not flat at all, right? It's so anyway. So it looks like we have something to worry about, it seems to me. But writing solubility product expressions. Well, to finish the greenhouse effect story, though, I mean, the ocean's going to reach its limit sooner or later, and then it's really going to have a problem. But anyway, writing solubility product expressions. Ksp expressions. So in general chemistry, we had a solubility table, and I don't know if you had this one or not, but it was something like this. So we answered questions like, is calcium sulfate soluble or insoluble? And you're supposed to be able to use the table, Monica, to do this. How would you answer this question, right? You had these tables for these ionic compounds, and you say, oh, that's soluble, or oh, that's insoluble, right?
What was the question?
Is calcium sulfate soluble or insoluble? So we got to find it in there somewhere. She says soluble. Now, do you agree, Andy? She sounded pretty confident. All right? So you got to find either calcium or sulfate. Now, these are all anions, so pretty much got to find the sulfate. So I think she did. She found it down here. Yes, soluble. Except you got to play the game, because you got to make sure it's not an exception, right? All sulfate compounds are soluble, except for calcium's not listed, so it stays soluble. Remember, that was the name of the game. Okay. How about calcium hydroxide? No. Yeah, we can ask that one first. Ida, is calcium hydroxide soluble or insoluble?
Insoluble, but it's on the exception.
It's insoluble. It's on the exceptions rule. So you should say that it's soluble, right? But there's an S here. So already life is getting more complicated, right? So it isn't a clear answer, yes or no anymore. There's degrees of solubility. So that's where this whole KSP thing comes in. No longer are we just going to say soluble, insoluble, and be done with it. Life is much more complicated than that. So fine, then what's meant by solubility? What's meant by solubility? Ricardo, what's meant by solubility? Oh, the solubility of calcium hydroxide.
The ability to at least dissolve in there into the solvent?
Yeah, the degree to which, he said, the degree to which it dissolves inside that solvent. Carbon dioxide's solubility in the ocean. Well, the degree to which it dissolves in the ocean. If it's highly soluble, then it'll 8 gigatons, no problem, per year. So that's kind of what we're interested in. So if we're talking about solubility, do you have to have a saturated solution, Kelly, to be talking about solubility? Would you have to have a saturated solution to measure solubility? Yes. The answer is yes. Right? because you need to have an equilibrium situation going on. You've already seen the little symbol, I think, that we're going to be messing with. And we know big K's are all what constants? Equilibrium constants. Well, equilibrium between what? The solid and its ions. So if the solid isn't there, this isn't going to work. So you need to have a saturated solution. Well, then it begs the question. Oh, I already picked on Ricardo. Gloriana, it begs the question, how do you know if a solution's saturated? How the heck would you know? By physically looking at it, how would you know?
You don't see any substance at the bottom?
You don't see any of that solid at the bottom. Then it probably isn't saturated. If this has been sitting here, which it has been, for over a year, it's saturated with calcium hydroxide, right? It's saturated. Now, it can be a trick question, though, because what could I do, Jeff, and still have a saturated solution but have no solid?
Heat it up.
Well, no. Well, just pour it off, right? Pour it off really carefully, or even filter it, right? You'll have this nice, clear solution, and it's saturated. There's no solid there, but I took it off of here, right? There was solid there, so it's kind of a trick question. See what I'm getting at, though? But to achieve that equilibrium, solid had to be there. Okay, so it's to achieve a saturated solution. The solubility product constant, i.e. the equilibrium constant for solubility reactions, Sabina, has the symbol Ksp. Okay. And the SP, Andy, probably just stands for what?
Solubility product.
Yeah, solubility product. That would be my guess, too. Okay, so if you have a equilibrium constant, you better, and they're all going to be tabulated. Calcium hydroxide has its own Ksp. Well, we're going to get different answers and do different calculations if not everyone writes the correct reaction that corresponds to calcium hydroxide's Ksp, right? 'Cause if you write the different reaction, you're going to have a different equilibrium constant. So everybody has to write it the right way. So what's the convention? How do you write, Jackie, these Ksp reactions? All right? Now, it has to be an equilibrium going on between a solid and its ions. So those things got to be in here, the solid and its ions. But where do you write what? You always write the solid where? Yeah, always write the solid over here, right? The degree to which the solid breaks up, that's the Ksp. And the reason why they do that, right, write the solid over here and its ions. I think the reason why they do that is because then it conceptually makes sense. If you have a bigger equilibrium constant, right, doesn't matter what the equilibrium constant is. If it's bigger, you have more what? Product or reactant. If it's bigger, an equilibrium constant. If it's bigger, you have more product or reactant. If it's huge, you have a lot of product because equilibrium constants are always products over reactants. So if you have a huge Ksp, people want to say, oh, that's really soluble, or that dissolves better than something else, right? So that's why they write it this way, solid going to its ions, I think. I mean, I don't really know, but it would make sense. Okay, but how is solubility calculated? Jeff, this is the $100 question, because that's all the homework. How do you calculate solubility? What's the solubility of calcium hydroxide?
It's product, like the products over 1.
Okay, well that'd be a start, right? You hear what he's saying? You'd have this Ksp, and it's all products over reactants. So you'd have the ions right up here, all the ions raised to any power if they're there, and it's all over 1. I agree with that, and this is the number, but it still doesn't tell us what the concentration of those ions are. And which ion, right? The solubility is the blank and blank. I wonder, is that coming up? No. Do you remember doing this? Doesn't matter what the reaction was. Ice. You remember ice? Tell me you remember ice. Gordon remembers ice. Jackie, you remember ice? Doing ice? Right? I was initial concentration. C was the change, and that's where our X's came in. And then E is the E for equilibrium concentrations. Good, so I is initial concentrations. We're going to make this little ice table. I is for initial concentrations, C is for the change in concentration, and E is the equilibrium concentrations. So all of your answers at equilibrium are really in this bottom row. And we'll do a bunch of these. If you don't remember, you will. But the point is that I'm trying to get at is solubility is always the X in ice. You set up your ice table, and then we're going to have to put in this whole equilibrium row, because Jeff got us halfway there. This whole equilibrium row, you put it into this Ksp expression, and then you just solve for X. That's going to be the game we're playing. Okay, so let's try one of these. What is the solubility of calcium hydroxide if the Ksp for calcium hydroxide is 5 times 10 to the negative 6? Now, where do you get this kind of stuff? These KSPs. Yeah, there's always going to be some table, or you Google it or something, right? So they're just equilibrium constants. So we want to find solubility. We want to find the X in ice. Okay, so that means we have to write a reaction and then do ice under it. So, Ida, what would be our reaction that we're interested in the first place? That calcium hydroxide, right, goes to, what are the ions? Calcium and hydroxide. Now, if you do this, you're going to lose a lot of points, because these aren't ions. So you got to write in the charges. Calcium is, now those of you who are saying +2, how did you know? It's an easy thing. Okay, here's one way, +2, because it's in group 2. The other way is to see it, just so you remember this stuff? The subscript, yeah. That is his charge, and this is his charge. Remember doing that? And the cations, a plus is always the first one, the negative anion is always the second one. Okay, so we got to do this. And then you should really have subscripts on stuff. And then the ions, we should write AQ on them, because they're always talking about they're dissolved in water. But it gets to be too much. So, but if it's an ion, it has to be AQ, so I kind of always leave them out. It just gets messy. But if you want to put AQ in for the ions, great. Okay, now we have to do ice.
Do you need coefficients for OE?
Oh man, I didn't even balance it. Didn't even move on. Yeah, we're not balanced. So how do I balance it? Oh, thank you, Ricky, thank you. Okay, ice. See if anybody remembers how to fill in this table. Okay, now there's a suggestion I have right off the bat. Kimberly, just put dashes, put dashes for what? In this, I mean, the big, showing it has nothing to do with anything. Down what column? See how there's 3 columns?
Oh, okay, yeah.
Put dashes where? Down which column? Right? Down the solid? Down the solid, because the solid isn't going to show up where? In any equilibrium constant expression. So if you ever see a solid or a liquid and you're playing this ice game, just right away do this, because it's a really common mistake. Otherwise you start throwing X's and you start doing stuff in there. No. These guys never show up. They're a solid. Remember, what doesn't show up in equilibrium constant expressions? What and what? Solids and liquids. So solid that never shows up. Who cares? Okay. The initial row. So you have to ask yourself, Danielle, do we have any calcium ions or hydroxide ions there initially? Right now, for you to say yes, that had to say something up here, right? That there was some there. Like it could say N 0.1 molar hydroxide, or it could say N 0.25 molar calcium, but it didn't, right? It's coming up in the homework. And when they do say something like that, you have to put it in the initial row. But they're not going to be that nice, just to give you a heads up here. They're not going to say hydroxide. They're going to probably say what? Does anyone see what's coming? Not hydroxide, but maybe potassium hydroxide. They're going to have this darn alkali metal in there, because that's the only way. You can't pull hydroxide off a shelf and make a solution of it. It has a charge. You can only pull neutral compounds off a shelf. And everything with as group 1 is always soluble, 100%. This is where your spectator ions come in. They don't do jack. The only purpose is to make a solid so you can make a solution of 0.1 molar KOH. So whenever you see that, my brain disregards this K part. Okay. The calcium. So for anions, to get them in solution, expect to see alkali metals, right? For cations, to get them in solution, so I'll have something to put in this initial row. What anions, if you're good at these solubility rules, you'll know this. What anions dissolve with anything? It has to be an anion. Does anybody know? Nitrates, acetates. But nitrates are pretty much where you're going to see. You don't see acetate very often because it has some acidic and basic properties that they don't want to mess with. So you see nitrate a lot. So again, nitrate is another thing where my brain, it doesn't even see it because it doesn't do anything. Its only purpose is to make that 0.25 molar calcium solution. Okay? So that'll be coming up in the homework. But it didn't say any of that. Danielle said it didn't say any of that. So you can put dashes or zeros, whatever you want to put here. Okay. Let's see here. Does Melissa remember how to do the change row? This is where the X's came in. Calcium would just be X. 2X, right? She just put the stoichiometric coefficient up front, right? Hydroxide is going to be changing twice as much as calcium because it has a 2 out front. X and 2X. Oh, here's another one we didn't fit. Is it positive or negative, right? Because these X's can be positive or negative. Is it positive over here, right? Because think of it this way. All you have is solid initially, right? It's going to break up a little bit. So these are positive numbers. Almost always positive, you're right. Right? There's a concept, though. And then to get the equilibrium row, you just add things up. So you'll have nothing plus X is X. Nothing plus 2X is 2X. Okay. Now remember, we're after solubility. And solubility, Desiree, is the what and what? Solubility is the helper. Solubility is the everybody. Solubility is the X in ice. Again, solubility is the X in ice. Just burn that in there, man. Because when they ask for solubility, oh, it's X in ice. You know exactly what to do. So now we got to solve for the X. Well, to solve for the X, we got to do what Jeff was heading upward, right? That Ksp, Let's write the expression, though. Let's not put in things yet. What would be the Ksp expression? Kelly, what would be the Ksp expression? Concentrations of products over reactants, so it would be calcium in brackets times hydroxide to the 2 all over 1. Perfect. Okay. They said the Ksp is 5 times 10 to the negative 6. No problem. Now we're supposed, this is an equilibrium constant. So these have to be equilibrium concentrations. Well, where are they in the ice table? They're in the which row? They're in the Gloriana? Which row are all my equilibrium answers?
In E.
Yeah, in E, right? E is equilibrium. So they're all here. X and 2x. X is calcium's concentration. Hydroxide is 2x. So X for calcium, 2x for hydroxide. So 5 times 10 to the negative 6 has to be what? 4x cubed? So what's x? All right. 5 times 10 to the negative 6. Hang on, let's turn on the lights. 5 to 10 to the negative 6. Divide it by 4. Take the cube root. What did you guys get? Did you get 0.011? Hopefully? Yeah, okay. Desiree and I got 0.011. So that's got to be right. Whoa. They said give the answer in units of molarity and grams per liter. What are the units right here? What are the units right here? Hopefully you got 0.011 in the first place. But what would be the units? Right. K is, look, you can tell what the units are. Brackets, or think of standard states. Someone said it. Molarity. Big M. Okay. So we got the big M one done, but now we need grams per liter. Grams per liter. .011 big M is the same as 0.011 moles over liters. Okay, so the question it comes down to, right, moles of what? Because if it's moles of what? And then you convert those moles into grams, we'll end up with grams over liters and we're done. But moles of what? Yes, the solid. It's moles of the calcium hydroxide. Exactly. So we've got a calcium. About 74.1 or so that I got. Take that times 0.011. I'd feel better if someone told me the answers. I didn't screw up. Andy, what'd you get? Anybody get an answer? 0.81 something? Let's go to 0.82. Yeah, that's what I got too. 0.82 grams per liter. So there's our two answers. So molarity, it's always of the solid. It's always of the solid. Okay.
Which one was that one for? The 0.82 grams per liter?
They wanted the solubility in units of molarity. We got it.
Okay.
They wanted the solubility in units of grams per liter. So start with it in moles per liter, convert the moles to grams, and you got it.
I just put my number on the wrong side. Thank you.
Okay. So are you okay with that? Jeff, make sense?
Yeah.
Alrighty, good deal. Which will be more soluble? Barium iodate or calcium iodate? Which would be more soluble? Gloriana, you have a game plan for that? Or a thought? Which would be more soluble?
We have to find the KSPs for both of them.
They gave us the KSPs for both of them. Do you have to find the?
Like, do the isotope?
Yeah. So I think what she was trying to say is you have to find the. Is anyone trying to fill in the blank? See what I'm trying to get at? Do you have to find the? Do you have to find the solubility, right? And you are correct. That's what makes this a trick question. Is you would think you could just look at the KSPs. Now, if it's a special case, you can just look at the KSPs. But if it's not a special case, and we'll talk about what the special case is, the answer always works if you calculate the solubility. Calculate the X in ice, and the X that's bigger will be more soluble. Okay? So that will work, but it's a lot of work. But let's check and see if this is a special case. If you went through all the work and you calculated your Ksp expression, right? They're all going to look like a number, right? This stuff, all over 1. They're both going to look like this. Are they going to be of the same format, right? Because you've got a barium and 2 iodates. You've got a calcium and 2 iodates. It's going to end up looking like this exact same format. You see that? So you really, because the chemical structures are the same, the chemical structures are the same, so they give you the same Ksp expression. Right? Now I just jumped to the Ksp expression pretty quick, and you might want to verify it on your own, but the point is that you'll end up with the exact same Ksp expression because the chemical formulas are the same format, right? 1 to 2, cation to anion. So you're going to have the same expression. So just compare the Ksp numbers. You don't need to go through all that work. Just compare these. The bigger Ksp is going to give you the more soluble answer. And the bigger Ksp is for which compound? The calcium iodate, right? It's only 10 to the negative 7. This is 100 times more insoluble. Or think of it this way, this is 100 times more soluble, right? So calcium iodate.
What's the charge on iodate?
Well, you can look right here. It's got to be a 1, right? Because this charge always goes down there. This charge always goes down here.
I saw how they switched. I was just making sure there wasn't like a ratio thing of like 4 to 2 or whatever, but I see how it couldn't be that.
Nope.
It would have to be like
Has to be exactly the same. Okay. So try 6-14. See if you can get an answer for 6-14. Find the concentration of the copper ion in equilibrium with copper bromide solid. And I'm giving you the Ksp. If I kind of lost you, just ask so I can help you out. Oh, that girl was really thankful that you found that in her book. You saved her like $30.
follow me along in class. You know what
I don't know why you have your cell phone on while you're in
I
class.
mean? I know. I know why.
The calculator, can we really divide it?
Yeah, I would divide by 4 first, and then the cube root is right there. You do shift that, or you can raise it to the 0.333 power, because it's 1/3. Because 1 divided by 3 is 0.333.
Okay.
So if you got the first one, go on to the next one. So I got around 8 times 10 to the negative 5. And then try the next one.
Yeah.
And if you got both of those, go on to 16. 16 is the real test, man. You can get 16. I think you can handle anything that's going to get thrown at you. Oh, this is, oh, here, remember this. Well, there's a trick here to part B. If you remember this ice stuff, you really shortened up your life. If you don't remember your ice stuff, you've got a quadratic equation here and you got some work to do. Okay? What was typically done when you wrote something like this? We had like 0.1 plus x. Yeah, we're dropping the x depending on what this k is. And there's a cutoff, right? 10 to the negative, yeah, it gets worse and worse. 10 to the negative 5 is great. Now, when do you want small k's are big negative number, like negative 9, negative 10, negative 11, or are small k's 10 to the negative 8, negative, what is this? How do you get smaller k's? More negative or more positive? More negative exponent. Excellent. So 10 to the negative 5 or more negative, they just say drop the x. Why? Because this is typically, pretend that 0.1 wasn't there. You'd have x times x. So essentially the square root of this thing is your rough concentration. And 10 to the negative 4, this 0.1 is huge in comparison to that x. So when you have these really small Really, really, that's a billionth. When you have these really small equilibrium constants, that means that there's hardly any product at all. It's essentially zero. All right? I mean, there's nothing there. So if you have these x's, there's nothing there. This thing doesn't break up. I mean, it does, but a billionth? That's negligible. So this is a billionth. Well, this is a tenth. A tenth plus a billionth is a tenth. So you don't need to do the quadratic equation. You just drop it. And what you can do is you drop that x there. You can't drop this one because you're multiplying by a small number. This is really important. You multiply by a small number, you get a small number. But if you take a big number and add a small number, you get the big number still. So make sure you drop the right x because it's a big deal. You're dropping this one that you're adding. And you go ahead and solve it, and you should go back and compare it to 0.1. And you'll see, it is really, really small. It's insignificant. So this really is equal to x times 0.1. And if you want to make it look correct, you should write like approximate sign. Or remember seeing this kind of thing and equals with a dot on it, right? And that'll look better. And then you can get your x. Take it times, let's see, divided by 0.1, that's times 10. 6.27 times 10 to the negative 8. I'm not sure if we even have one. Because it's usually what Monica just said. Is what the ones you're interested in, the homework is really interested in with KSPs that are 10 negative 5, negative 6, negative 7, you almost always drop the x. So I don't know if there even is one. Now what you can do is, notice how these problems are kind of fast. You can kind of zip through them. Before you hand in your quiz, this answer that it's in the presence of 0.1 molar sodium bromide, this answer should be, the solubility should go what? Down or up? If you have some of the sodium bromide in there.
Yeah.
It should drop like a rock, right? Because now you have all this bromide in there. That's whose principle? It's going to shift this way. Le Chatelier, or something like that, right? It's going to shift towards reactants. So this has to drop like a rock, and it did. It dropped by a factor of 1,000. Went from 10 negative 5 to 10 negative 8. Okay, so. And they didn't care about grams per liter or anything, so we're done. Just leave it at molarity. Try 16. If you didn't quite get B, if you're not sure about it, just ask. Yep. Yes, that's the trick. That just goes right there. Exactly. You might be a little bit confused. I don't know if you are, but it says find the concentration of copper. It doesn't say find solubility. Will an ice table still work? Yeah, because you just look in the E row under copper and you're done. That'll be your answer, right? You solve for what's under copper. So you definitely have to do an ice table. Before you start doing some math and getting all mad at me, let's make sure. Sabina, what does this mean? Hydroxide is fixed at 1 times 10 negative 6 molar. What does that mean for our ice table? Well, not only would it be the initial, it's also the E. It's the E. Right? Because it's fixed. So right off the bat, you know the equilibrium answer for hydroxide. And you don't multiply it by 6 or anything like that. I mean, they said this is the concentration. So that's what you put in right under the hydroxide. Okay. Now the others you still got to work on. The hydroxide is fixed at 1 times 10 negative 6 molar, so that's what you have to use. So Andy, it looks like to get my concentration of copper as a final answer, what would you have to do?
You just plug in 1 times 10 to the negative 6, and multiply it times 4x and x.
Yeah. In the end, you're talking about all the math, and you're going to solve for x, and then multiply it by?
Multiply x times 4.
There it is. You hear what he said? You got to solve for x, doing what he started to get into with the Ksp expression, and then multiply it by 4, and that will be your copper concentration. So that's the big picture. Solve for that x, then multiply it by 4. So I'd write the Ksp expression so you don't screw up here. So what you do is you have to raise both sides to the 1/5, right? And 1 divided by 5 is 0.2. So you need to raise this to the 1/5, or 0.2. And that's what that x to the y is. So you just plug this in, and then push that, and then 0.2. So this is a good calculator problem. Make sure you can get it.
So for the concentration of hydroxide, is that 6 in there?
It has to,
1 point?
what I have for my concentration of hydroxide, I have to raise it to the 6th power.
Oh,
Well, what's my concentration of hydroxide? There it is.
Ah.
It has to be that to the 6.
I thought it was like this is 9,
Okay.
right? I can't see anything. What?
Sit up front.
Oh, okay, I see it.
It's ugly. So did anybody get that far? Monica, is this what you got when you had x to the 5th? Was it this number?
Yeah, but I didn't.
Hmm. Anybody get this number to x to the 5th? I want to make sure. You did? Yeah, before x to the 5th. Okay, good. So 2 of us got this, so this should be right. So at some point, you should get to this far. You'll have x to the 5th equals some number. So I had to take that 2.3 times 10 negative 69, had to divide it by 256, had to divide it by 1 times 10 negative 6 to the 6th power, and I got this. So so far, everything on this calculator is straightforward. Okay. There's just one more step. Make sure you realize this. If you have to raise both sides to the 1/5 power. That way you'll get x. And to raise anything to any power on this calculator, it's that x to the y button. So I'm going to put this number in, 8.984 times 10 negative 36, and raise it to the 0.2, because 1/5 is 0.2. And you get about 9.8 times 10 negative 8. Is my solubility. Okay. So make sure you can get all that on your calculator there.
So we don't multiply by 4? Oh yeah, that's just x, right?
Well, that's just x. Oh, shoot. Thank you. They wanted copper. I asked Andy all that stuff. I didn't do it. Right? They wanted copper. And then copper is times 4. Thank you. About 3.9 times 10 negative 7. There, thank you very much. Should be brownie points for that.